In topic 7 now of chapter 2, we're going to take a look at polynomials and rational inequalities. Here are the objectives, pretty straightforward. Now, again, instead of equations now, we're looking at inequalities which deal with whole regions of solutions. And here are the most obvious: less than 0, greater than 0, less than or equal to 0, greater than or equal to 0. We'll look at the general points for solving polynomial inequalities. We express it as a function as either less than or greater than. We want to solve for the boundary points, which we'll go over. We locate these boundary points on a number line, thereby dividing the number line into intervals. And then we're going to choose representative numbers called test values. And then we want to see in which position these test values fall. And then we will write the interval notation for what we see. All right, we're going on now to example 1. Now, notice this is going to be a quadratic. So as we go to solve it, the protocol, of course, is something we had much earlier. We're going to take our 20 here, move it over to the other side, so we have it in standard form. We're then going to solve it. In this case, it factors, so by factoring, so we get x is 5, x is a negative 4. Now, what's our next step? Well, put them on a number line. So once we put these values on a number line, our negative 4 and a negative 5, we can see the boundary points divide the lines into 3 intervals. Now remember, since this is greater than, the negative 4 and the 5 are not really in the system. That's why they're using parentheses for these. So now what we need to do is, what are some boundary points to make the statements true? We're now going to use the test value of a negative 5 to check on this interval here. That is from negative infinity to a negative 4. Remember, negative 4 is not included in the system because of this inequality sign. So when we put 5 into the system, it does equal 10, which is showing that that is less than 20 here. So this makes it a valid area of solution. Now, when we go to our interval between a negative 4 and a 5, we're going to use a test value 0, which on the number line is between these. And we find that our answer is a negative 20. Well, that is not in the area of solution. So there are no values for this inequality in this area. So this area is empty. When we go to our third region, which is 5, and again, 5 is not included because of the parenthesis, to positive infinity, a test value would be 6. We put 6 into our system, and that meets the requirement. So what is our area then? So in solving this inequality, we find that our value goes from -4 off in this direction, goes from a +5 in this direction, and there's nothing in this area. So writing this once again in in interval notation, it's coming from -infinity up to, but not including, a -4, and then in union, starting at just beyond 5, 5's not included, to +infinity. We'll now take a look at rational inequalities. Again, we're thinking here basically the form of fractions. Now, for example 2, here's our inequality, and it's in a fractional form. Now, one of the things we want to do is to get our inequality equal or on one side to a 0. So here we have it. We're going to take this term, move it to the other side, where it becomes a -1, as we see right here. And now that's greater than or equal to 0. Now, we have to work with this to get it to be a fraction, in a sense, over this. Now, how do we do that? Well, we have to take our -1 and give it a denominator of x plus 1 so we can do our subtraction here. That involves multiplying this -1 by 1 in the form of something that will make a denominator x plus 1. Well, if we multiply both sides by x plus 1 over x plus 1, this is a form of 1. And that's what they've done here. So now we have a common denominator, and we can take this sign here and move it up there, which is what they've done here, and now put this all over our common denominator. We can then remove the parenthesis, which is what they're doing, by making this x negative and this 1 negative. So we started with this, and when we moved the 1 over and did some fancy algebra, we found out that this and this are equivalent. This is equivalent to this, where in this form we know that these, if we equal each of them to 0, we're going to get to our next step, which is let the numerator is going to be x is equal to 1, and our denominator x is equal to a -1. This sets up our boundary points on the number line, and we'll see that in the next slide. So we know this has the boundary points of this. Now what we want to do is see where do values here, trial values within these areas, make the statement true. Now our boundary points, as we did earlier, would be for this portion, this in interval notation, this. Now keep in mind that here, because it's greater or equal to 1, 1 is now in the set. That's why we're using a bracket. And then using a bracket 1 to positive infinity. Normally you would write this like a little circle here, hollow. This one filled in. Now here we continue to put in our test values. And for this, we're going to choose a -2, which is within there. Putting that into this function, we see we end up with a 3, which is greater than 1. So this is a value. So this portion is true. As we use a test value that's in the middle, we can choose 0. Now, when we put a 0 into this, the results is a -1. Well, -1 is not in this set. So therefore, this is not an area of solution. And when we go to our last part, where we look at from a 1 to positive infinity, choosing a 2, we end up with 1/3. Now, they're not showing us this, but if you put 1/3 into this, 1/3 here and 1/3 there, this actually makes this side a 1. 1 is equal to 1, so this portion where we find the 2 is also valid, which is what they're indicating here, but not showing us how they got it. Okay, so in plotting this then, on our graph, we would use a parenthesis at -1, going off in this direction. That's our boundary point. And then 1 is actually included in the set. And we write it in interval notation this way. And also they're showing us set builder notation, with the OR indicating the union. All right, one more example. Here we have an example in the form of a word problem. An object that is falling or vertically projected into the air has its height above the ground, which is this value, in feet given by this function, where v sub o is the initial velocity of the object in feet per second. T is the time that object is in motion in seconds. And S sub o, this one here, is the original height of the object in feet at the time. So let's take a look at the specifics. So for example 3, they're setting it up with an initial velocity of 80 feet per second. Again, we don't know the time. In which time interval will the object be more than 64 feet above the ground? So our ST is going to be greater than 64 feet above the ground. That's our initial inequality. So what we want to do here is find what T is. So what they're doing is going to take this 64, transpose it to the other side, where it becomes a negative 64, and then find our boundaries, which is solving this for the zeros in a sense. So notice the protocol they're following. They're going to factor out a negative 16 out of each of these terms and get this. And this factors nicely into this. Equate each of the factors to 0, and we get t is a positive 1, and t is a positive 4. Now, what does this mean? Well, let's go to the whiteboard for just a moment here, and I can show you a picture of it. We have a parabola that is forming. That's the nature of that equation. And then at 1 second here, this is a 1, and then this is a 4 in our graph, that this projectile will be above that stated amount of feet. Okay, there's a little visual there. Back to our screen. And when we put it on our number line, we see these are our values. And then we want to see which ones would make it true. So in a sense, these are ordered pairs that we're going to then put into our equation here. And the one that makes it true is this set. So prior to that, it's not true. This is not true. And this is not true. So this would be our region of solution. And that winds up this lesson.